Okay. Do you see the screen well? Yeah? Perfect. Okay, so I titled the talk today, Mineral Reactivity, Surface Environment, and Lightning Strike, because I'm a mineralogist and crystallographer by training, and most of my focus is related to how the mineral behave structurally, so at the nano scale, when they interact with a solution that has a different pH, or they interact with an impact like a lightning on a rock. And we will see today 3 examples of the type of research that I'm doing. And let's start, and I'll show you what I'm talking about. So I have 3 different research projects that I ran since I was a PhD student. And one is about the mineral surface and the feature and the factor that can affect the crystal chemistry from the bulk to the surface. The second one that I started at the Smithsonian Institution was about the reactivity of manganese oxides, because manganese oxide are very widely used, and there's a little known on the properties at the crystal chemistry level. And when I say crystal chemistry, I mean so that I'm looking at the chemistry, so the elements that I have in the structure, and the crystal structure itself. So I combine the 2 components and see what happened at the atomic level. The third project is about the reactivity of minerals to reconstruct the environmental extreme condition when a lightning strike on rocks. So I look at the fragment of minerals that can be embedded into the glass and see if there's any evidence of shock impact. And when I say shock impact, I mean changing the temperature and changing the pressure that can help me to reconstruct what happened in the system. Okay, so the first project is about the mineral surface and the factor affecting the crystal chemistry. I focus in particular on my favorite mineral, that are micas. Micas are sheet silicates, so it means that they are made of layers, like a set of paper sheets, one above the other. This sample here is a pseudo-hexagonal perfect mica, and you see that the surface of micas are very flat and nice to study, and also they are very common in nature, so that's why I decided to choose this group of minerals. So first at all, we needed to define what is a surface, because most of the time when we define a mineral, we say that is a 3-dimensional pattern that is mostly infinite. Well, it's not completely true, because there's always a surface of the mineral that is in contact with the environment. And the surface is the external boundary of a solid in a vacuum or a gaseous environment. So anytime that is a surface is in contact with the environment, there could be some changes. If you see here in the bulk structure, you have this repeating pattern that is the definition of a mineral, right? So we see the atoms, a specific distance. In this case, it's a 2-dimension. And you see this layer, that is the surface. So in this case, the layer of the surface is not affected due to any change. And the distance that is usual in the bulk is the same at the surface. If you have a change on the surface, let's say a change in the pH or in a solution, in that case you can have a relaxation. Let's say that at one point the bonding in your surface layer are breaking. So at that point you have an imbalance of charge in that layer, and a relaxation occurs. So the first layer, the surface layer, will have a shorter distance between the bulk arrangement. In a case of a reconstruction, it's a completely change that you have at the atomic level. And in that case, you have a breakage of the bonding, and in that case, reconstructions, recreation of new bonds that make the structure stable. So in a case of relaxation, it's more like a shortening or a bonding that is making longer distance, but most of the time is a shortening of the distance of the layer compared to the bulk. So there are three different possibilities of a surface, depending on the interaction and the reactivity that they have with the environment. So what is the goal of this research, comparing the structure of the surface and comparing the structure of the bulk? Because we want to understand and shed light on the relationship between the chemical composition and the atomic structure at the surface and at the bulk, in particular of micas. And because these reconstruction and relaxation that can happen at the surface are a change also of the chemical and physical properties of the mineral. So based on that, there's an improvement of the knowledge of the structure that can help also possible application in several fields. What are micas? Micas are aluminosilicate layer mineral. They have a set at the atomic level. You see here, they have a set of layers that have a single tetrahedra that are linked together, forming an hexagonal pattern. These apex in the tetrahedra are linked with the apex of an octahedral layer. And then there's another layer of a tetrahedra. So it's called a TOT layer. It's like a sandwich, as it's lunchtime. So let's think about this TOT as a sandwich. Between these TOT, there's a big gap that is called the interlayer, where we have big cations that are linked with the apex of the octahedron here. So the interlayer is the link with the TOT by van der Waals bonds, so weak bonds. And it has a negative charge because you could have some substitutions of cation in the tetrahedral and the octahedral layer. So all of these charge imbalance is rebalanced with the interlayer cations. Okay, so you see that they have a very from long formulas, and you see that the silicon can be replaced by aluminum. Sometimes the aluminum in the octahedral layer can be replaced by magnesium or iron, and also the cation in the interlayer could be potassium, calcium, or sodium. So they have similar charge, but depending on the substitution that you have in the TOT, you can have a different set of cation in the interlayer. But if you see here, you have van der Waals bond in this spot. So you know, you can imagine that as you have ionic bonds in the TOT, the splitting of the layers will be along the interlayer. Okay, so this is the structure of micas, and that's the mineral that we are gonna study. In this example, you see here a layer, a set of layers of muscovite. The techniques that I used were different from the bulk and the surface. For the bulk, I use the single crystal X-ray diffraction. So I use a little fragment, and when I say a little, is like 0.1 millimeter in diameter of a mica. And I studied the structure of this mica. And then the electron microprobe analysis is for the chemical analysis. So how much of these cations I have in the structure, and if there's any substitution, what kind of substitution. So the electron microprobe give me the information of the chemistry, and the single crystal diffraction, the information of the structure. And then I put together this information to define the structural formula of the mineral. We'll see later about that. And for the surface, I use a technique that is called X-ray photoelectron spectroscopy. The abbreviation is XPS. So that's the method that I use. And generally the approach is to use several methods so that we have a bigger picture and a complete picture of what happened in the structure. Okay, if you see in this picture what I said before at the macro scale, the mica is forming layers. So anytime that I create a surface, a clean surface to study the crystal chemistry, I cleave the mica along the interlayer. So mostly what I'm saying is splitting the layers on one side and another. And that is mostly what I'm doing. Any time that you have a mica, I know that the temptation is to splitting the layers, and I'm sure that your professor said don't split a mica, but I did that for years and for studies, so it's okay, I can say. For this kind of study, if we study the surface. Okay, so why study micas? Because they are very common in nature. You can find them in soils, you can find them for fine applications. They are a counterpart of the fine grain clays, because clays are layer minerals, but you see here this example of kyanite is really fine grain. So making a study of the surface of clays is quite complicated. So that's why we use micas as a counterpart of the surface of a clay. There are several kinds of micas. Depending on the cation substitution that you have, and you see they have different colors depending on the substitution that you have in the structure. So there's many processes that happen at the surface, and that's why we care to study the mineral surface. There's an interaction with the acidity of the soil, for example, or the water solution that can be in contact with the surface and generate weathering. And then you also have weathering with several sources. But the surface are also important to drag delivery. So that's why we are studying micas and clays, because clays are generally used even in pharmaceutical Micas are also used in cosmetics, so the surface of micas can reflect the different colors. And for the same principle, even the paint that is used for cars, that has this sparkling bright color, generally have micas that are coated with colors. So that's why the study of the properties at the nanoscale are important to develop new materials. So the sample that I considered in this study were the sodium muscovite from Antarctica, iron-rich fulgurite from Russia, and an iron-rich polylithionite from Greece. You see these long formulas with these nice little numbers here. This is a structural formula, so it means that it's put together the information of the structure and the information of the chemistry that I collected with the single crystal for the structure and the microprobe for the chemistry. So based on this formula, you see also these Roman numbers. Those are the site, so where these cation are sitting in the structure. So this is the coordination of the cation in the site. And you see the potassium and sodium is in the interlayer. All of these substitution for aluminum are in the octahedral layer. And the aluminum is also substituting silicon in the tetrahedral layer. And then you have oxygen, fluorine, and OH as anions in the structure to balance everything. So these big formulas to collect the crystal chemistry and put together the information specific for the sample that we study. If we move at the surface, at this point, we collected the data of the bulk. We know the crystal chemistry of the bulk, but we want to know what happened when we split a layer of a mica, and if there's a reconstruction or a relaxation of the surface. And to do so, we use the X-ray photoelectron spectroscopy that survey the chemistry at the atomic level when an X-ray source interact with the first 10 nanometers of structure with these X-rays. So anytime that you have an interaction with X-ray, you have a photon jump outside, an electron jump out of the orbitals in that specific atom. So the XPS is surveying these electron jump, and that's why you get the information about the specific atoms and the surrounding about these atoms. In fact, you see here the 2s, 2p. So these are the orbitals where these photons, these electrons are jumping out. And so we have the information about the local bonding of the atom at the surface. Why at the surface? Because compared to the X-ray diffraction, the angle of incidence of the X-ray is 45 degrees. So it's lower and less penetrating to the bulk. Okay, so this is what we can get with the photoelectron spectroscopy. That's a lot of information at the surface, because we know what is the surrounding and around the specific cations in the structure. And based on that, we can know if there's any reconstruction or relaxation. Here the result. So we look at each element in the site, And we notice that the silicon has a binding energy that is consistent with the tetrahedral coordination. And that is based on the energy that is used for calculating the jump of the electrons in the 2p orbital of silicon. Same for the Fulgurite. So most sample maintain this coordination in the T layer. The aluminum distribution is more complicated because you notice from the formulas that the aluminum could be in the tetrahedral, but also in the octahedral layer. So how do you know the binding energy of these elements? Well, you can consider the charge distribution. So the energy that is change if the aluminum is just a metal, tetrahedral or octahedral. And you see there's an increase of binding energy, increasing the amount of anion that are surrounding the cation. And in my case, the binding energy is between a tetrahedral and octahedral. So part of the aluminum is in the tetrahedral and part in the octahedral. So even in this case, at the surface, this substitution is maintained. So there's no change in the TOT layer at the, based on this data. And if you see here, the binding energy is increased slightly compared to the polylithionite and the muscovite because of the cation substitutions that occur in these two minerals. And in the polylithionite, you have iron that substitute aluminum in it. So all these substitutions generate a shift in the binding energy. Even for the iron, you know that the valence state of iron is a 2+ and a 3+. So even in this case, it's possible to distinguish the two components into the binding energy of the shift of the peak. So the shift of this peak can give the information about the reduction and oxidation state of the iron into the structure. And the binding energy from the metal iron change and increase based on the valence state of the iron itself. And that is based on the coordination of the iron in the structure. So what kind of, because I told you that the anion that you have in the structure is not just oxygen, but you also have fluorine and OH. So based on the binding energy, it's possible to discriminate the valence state, but also understand if there's any clustering in the octahedral layer. And there are, because we noticed based on the binding energy of the 2+ and the 3+ iron, we noticed that the preference is with the OH. So we were able to notice that there's more organization that is what thought before. Before these studies, it was thought that there was a random orientation of the fluorine and OH in the apex of the OH, but it's more organized than it's thought. The magnesium is a substitute of iron in the octahedral layer site, and you see that the binding energy is more close to the fluoride binding energy, magnesium fluoride. So the iron prefer the octahedral layer, the octahedra with the OH in the apex, and the magnesium prefer the fluorine. So there's more organization in the site that is was thought before. Other story for the interlayer, we can have potassium and sodium as a substitute. The coordination of this site should be 12 in the bulk, but at the surface it's 8 or 6. It means that there's a relaxation of the layer at the surface anytime that you split these layers. So anytime that you create this imbalance due to the peeling of a layer, what happened at the atomic level is a generation of a relaxation of the site, and later on a reconstruction of layers of charge that is related to the link with the molecules that are in the air, like water and the CO2. So that's the binding energy and the coordination that is possible to extrapolate from these peaks. And these peaks define the electron jumps in the XPS. So we lost we relaxed the layer, and we lost some of the potassium on one side of the layer. So most of the potassium oxygen are producing this relaxation, and then this distortion in the coordination is rebalanced with the link with the CO2, oxygen, and water that is in the air and in contact with this surface. So if we place the clean split mica in a solution with a different pH, we will see that due to this relaxation and this imbalance, we will have a reconstruction of bonding, and the surface will be different than the bulk. Okay, so based on these studies that are related to the reactivity of the crystal chemistry of micas, another project I focused on was on the manganese oxides reactivity. Manganese oxide are very common, in particular in Virginia. It's possible to notice these dendrites in sandstone and sometimes in limestone too. They are black in color, and they are super common in soil like micas. And they are called phyllomanganates because they are forming layers. So in this case is not a TOT, but is just one layer of octahedra with the manganese 3+ and 4+ into this layer. Manganese oxide are key components in sediments, and they are very reactive with any big molecules that could be in the environment. And so they are good minerals that are widely synthesized for catalysis and also for energy storage, and also for environmental purposes. In my case, I synthesized the manganese oxide to understand the structure, because it's unclear how this substitution of the cation in the interlayer and the water happen when a pH change occur in the solution. So I studied these two structures. One is the triclinic that is more stable at ambient condition, and the hexagonal H Birnessite that lose the cation in the interlayer, and there's a generation of vacancies that can be replaced with a manganese 2+ the manganese 2 plus is generally more stable in aqueous solution. So most of the time the substitution is also with the manganese 3 plus. This happened when there's a change in pH in the solution. In a more acidic condition, we can have this change in the structure. This change is also made possible because there's a stretching in the octahedral layer due to the Teller distortion of the manganese 3 plus site. So based on this stretching, at one point we have an imbalance in the charges and a regeneration of a new structure that is more stable for the new conditions. Why we are doing this? Because we want to explore the chemical and structural changes in the Birnessite. And during this change, we want to know what happened to the structure. And mostly it's because it's important from an application point of view that the cation exchange needs to explain this transformation in the structure for understanding the chemical and physical properties of the changes. In this case, we use different methods. We use laboratory synthesis, the ion exchange, the powder diffraction to look at the structure, the SCM, and Raman. So we use several techniques for arriving at this black material that is nanocrystalline, super dirty, but very powerful from a chemical and material science point of view. So what I've done was studying the evolution of this reactivity. So study the evolution of the crystal growth, and I selected the mineral that I was synthesizing every hour and every 5 minutes, 10 minutes during the process. And I noticed in this way the evolution of the phases and the growth of this crystal over time. And the result after 5 hours of synthesis is the Birnessite, that is the Phyllomanganates that I need for my experiment. So I placed this Birnessite that was dry and studied with X-ray diffraction into a solution of the cation chlorides at different molarity, so that I was able to study this cation exchange with the calcium that is a common element in soil, and it's one of the components of this substitution for catalytic purposes. With the cation exchange, I did different pH of this solution, and I noticed that changing the pH, the calcium Birnessite, the structure change from a triclinic to hexagonal. So it's more a structure that is between a triclinic and an hexagonal, but definitely more close to the hexagonal Birnessite. So we notice that the exchange is not affected by the cation in the interlayer, but is affected by the pH of the solution. In the calcium Birnessite at pH 9, you also see this extra peak. This is the calcite. So it shouldn't be there, but it was synthesized because of the reaction of the CO2 with the solution, and there was a precipitation of calcium carbonate during this exchange that it didn't happen at the lower pH. So this is another picture of the different molarity. So even with the different molarity, you notice that the exchange is not affecting itself the structure. Mostly it's the pH that is affecting this structure change. So it's mostly related to the acidity of the solution rather than the cation exchange itself. That's the morphology of the Birnessite at a very small scale, 3 microns. And I use these scanning electron microscopy with the EDS analysis to verify that the exchange was complete. And after 5 minutes in the sample, after 5 minutes, we noticed that the exchange was complete. So the exchange is extremely fast. It has this flake-like structure, and regardless of the pH, the morphology is maintained. The Raman spectroscopy confirmed what we noticed at the X-ray diffraction, and even in the case it noticed that the lower calcium concentration at pH 3 and all sample at pH 2 switch on a structure that is more hexagonal. So we determined the relationship between the interlayer cation, possible contaminants in the solution, the crystal structure, and the manganese oxide. So we shed light on the mechanism that generate a change in the crystal chemistry and the properties of these objects. The last topic that I want to cover is the natural and artificial fulgurite. This is a very unusual topic for the mineral reactivity. So fulgurite are natural glasses that are formed by sand, rock, and soil that is struck by lightning. The major type of fulgurite are the sand fulgurite and the rock fulgurite. For this project, I focus on a rock fulgurite. Why we want to study this? Because they are these fulgurite are a record of the condition that occurred when the lightning struck the surface. So these kind of protocols can be extended to other shock impact events like meteors, craters that are subject to weathering very easily. Okay, so the goal is providing insight on the processes that happen in extreme condition and in non-equilibrium conditions. With the same techniques that we use here, powder diffraction, microprobe, petrographic microscope, and SCM. The fulgurite that I studied was coming from Mount Motarone, that is in the north part of Italy, in the Alps. And it was above a well-known pink granite that is famous because it's used for several monuments in Milan. The rock fulgurite was a black coating, glassy, in texture above the rock, and you see that the quartz that is generally very smooth at the microscope has these fine cracks that are close to this black coating, evidence that there was a shock. And at the electron microscope, you see that there's some fragments of residual minerals that came from the rock when the lightning struck the rock. So based on this glass matrix, but in particular the minerals that were embedded and frozen mostly into the glass, I was able to reconstruct the condition when the lightning struck there. I developed a new protocol for the X-ray diffraction to study these kind of material, because it's not a lot of glass that you have on the top of that. Is few micron of sample, so it's not enough for the usual stage for the X-ray diffraction. So I filled these very tiny capillary of fine powder, and I studied the sample based on a new capillary mode analysis. And the result was to notice that we have glass, of course, and we also have residual phases, and in particular phases that are of high temperature, that is the cristobalite. Based on this pattern, I was able also to quantify the phases, residual phases into the glass. The glass, of course, is 80%, but I also have a very high percentage of cristobalite that is unusual to find in a sample at room temperature. Evidence that there was a change in the temperature of the system. I also noticed that the color was this black coating. It means that there was something on the surface of this granite. It was weathered possibly, and it pearlized at 350 Celsius. So it's mostly organic matter that was on the surface of the granite, and it burned at the moment when the lightning arrived on the rock. So based on this information, I reconstruct the system, and I was able to calibrate the temperature of when the lightning strike the rocks. But it wasn't enough, because I was looking at the end process, but I didn't know if that was the beginning. So it was the point where the lightning fall down. So what I've done was an experiment in the lab, and recreated the lightning on the rock you see here, so that we were able to study this rock and the fresh fulgurite on the top of it in the lab. And the result was this evidence of a glass crater that was forming on the surface of this rock. We tried with a dry surface and a wet surface, because you noticed before that the glass had a lot of porosity. So we noticed that probably the granite was wet at the moment of the lightning strike, because when the surface is wet, you see a lot of bubbles on the top of this glass. And it's looked like an explosion. So most of the glass is creating this rim on the surface of the rock, like in this example. So a lightning arrived to the target rock, it generated this crater and vaporized a few layers of the rock, and created this shock wave that is cooled down pretty fast and generate a glass on the target rock. And that is mostly what happened as an explosion or a shock impact in general. We also noticed that on the top of a fresh granite, when we struck the lightning, it was slipping on the rock and falling to the ground. So we noticed this because the granite was rich of biotites, and those biotites are insulators, so mostly they are not conducting any electricity. So if you have a fresh granite, generally there's no conductive layers, and the lightning does not occur. So summarizing the talk here, we have explored the reactivity from the surface to a very high temperature. So we noticed that the micas has an imbalance of charge anytime that we split them. And this reduction and distortion of coordination generate more reactivity at the surface, attracting molecules on that. And that's why they are used as a substrate for studying living matter, for example. The Birnessite has a reactivity in the crystal structure anytime that you have a change in pH in the solution. So we were able to get more insight on the crystal structure and the cation exchange properties of this group of mineral. And for the lightning rock interaction, we recognize the path of a lightning through a basalt and through a granite, and the reactivity that the reaction that happen when a lightning impacts these rocks. And thank you for your attention, and I would be happy to answer any question if you have any. Thank you.
Thank you, Chiara.
Thank you.
All right, questions for Chiara. We had one in the chat.
Oh, let me see.
Did you run any tests for higher pHs? I saw that for most of the data, you just went from 2 to 9. So I'm curious if there were any different results for the mineral when it was in a more basic solution.
Yeah, in a more basic solution, you notice the cation exchange, but the structure is maintained like triclinic. So there's no change in the structure. The exchange happened, but there's no modification in the structure. The structures started to move from triclinic to hexagonal only when it's in the acidic pH. When you are in the more basic pH, the structure is more stable as a triclinic. Yeah, and in the acidic situation, you also lose the calcium as exchanger. The water is more into the structure, but you still have a little percentage of calcium, but more water than in an unusual basic pH.
I have a question about the mica stuff. Do you have any thoughts on why the magnesium likes the fluorine site as opposed to OH?
I don't know. That's a good question. But I was so excited to find that there was more organization. That is what thought that this is a good question. That will be the next chapter. Thank you for that.
Okay. I think a lot of folks have a 1 o'clock class, so they're starting to exit here.
Okay.
Any other questions for Chiara? All right, I think that's it for questions. So let's thank Chiara.
Orion might be raising their hand.
Oh.
Oh.
Who was that? Orion.
Yeah, I was just wondering, what was the most surprising thing you learned through your research?
The most surprising, sorry, I missed the second part.
The most surprising thing you learned in your research?
Oh, well, for the micas, it was exciting to know that it wasn't a random orientation of these cations. So based on this clustering, it's an important information if you are studying the physical properties of these minerals. For the lightning strike, that was surprising that I study a granite, a natural granite, and in the lab, I wasn't able to replicate that. And I was like, that's interesting, because I was expecting to recreate the condition of a lightning strike in the lab on a granite. And that was surprising to notice that the granite needed to be weathered to conduct electricity and be struck by this lightning. And also the very exciting part of research for me is to design the protocols. So to develop new protocols to find and solve puzzles like this reconstruction of the surface, find what happened if you change the condition, and see the evolution of these changes over time, like in the Birnessite experiment. I was very into the understanding of what are the steps and how long it takes to make these changes over time. Yeah, the lightning in the lab, we were amazed. We found a line on the bottom of the sample, and we noticed that the part of the insulation of the sample stage was melted. So we noticed that it was really slipped on the ground. And the evidence of this slipping, it was, there weren't any crater or any evidence on the top of the rock, but it was on the bottom. So we were like, huh, okay, that's happened. All right.
So what if you did it with a nice piece of weathered granite?
That's what we are testing now. We are trying to test the weathered rock so that we can understand if we have this conductive layer of the organic matter. Because we thought anytime that we want to study an insulator in a SEM, we generally coat with carbon. So we thought that it was probably the weathering to make the change.
Right, I think we should probably wrap it up there because people have class at 1 o'clock.
Oh, okay.
Thank you again, Chiara. It was wonderful.
Thank you for having me here.
I'll stay on a couple more minutes.